Oh, I am sorry. I am sorry. Sorry. So let me just go over. Uh, so I would like to show 2 implies 1. So let U be an open subset of Y. I would like to show that F inverse of U is open in X. Okay. So that was condition 1, the definition of being continuous, right? So F is continuous. I would like to show that 2 implies 1. Okay. And this is how I will proceed. Okay, so I would like to show that F inverse of U is open. So let B be the complement of U, which is a closed subset of Y. And Y is the disjoint union of U and Y minus Y. Then X is the disjoint union of this this subset. X is the inverse image of Y, and we have this 2, which is a disjoint union. This joint union. And note the following. So by condition 2, F of inverse image Y minus U closure. So I take this subset, take its closure, and look at its image. I know that this is contained in what? This is contained in the image of this set closure. But what is this? You look at the inverse image of something and then you look at its image. Well, that is of course contained in Y minus U, right? So inverse image of something and then you look at its image. It is contained in this set. It may not be equal to this, but it is contained in this one, and you have closure. But this means what? This means, well, U was open in Y, therefore Y minus U is closed in Y, therefore this is Y minus U. So since U is open in Y. But this means what? Image of this set is inside this set, therefore whatever this thing is, in particular şu var elimde. F inverse Y minus U'nun closure'ı F inverse Y minus U'nun içinde. Bu da ne demek ama? Yani bu küme zaten bunu içeriyor. Çünkü bu bunun closure'ı. Right? This set is already containing this one because this is the closure of this one. But we see that closure is contained here. Hence, they are the same. So F inverse Y minus U is equal to its closure, so that this set is, so that F inverse Y minus U is closed in X. But this set and F inverse of U, right? F inverse U and F inverse Y minus U are their complements. This is a disjoint union. And I know that this one is closed. Therefore, this one has to be open. Thus, F inverse of U is open in X. So we are done. Okay. We showed, so far, we have shown 1 implies 3, 3 implies 2, and 2 implies 1, right? Bakalım bir daha. So we showed 1 implies 3, 3 implies 2, 2 implies 1. Okay. Hangisini? In particular dedik. Ha, şunu. Şöyle. Bu kümenin görüntüsü y eksi u'nun içinde kalıyormuş. O zaman bu küme y eksi u'nun ters görüntüsünün içinde kalır. Böyle sorunca benim de kafam karışıyor. Okey. Var mı başka sorusu olan? Okey. Well, because they are complements of each other. If you have two disjoint sets, and if they are giving the whole space, suppose they are disjoint. So B is then x minus A, and A is x minus B. So if one of them is open, the other one has to be closed. Uh-huh. All right, so there is this 1 implies 4 and 4 implies 1. Yeah, that's kind of easy. Let me give this as an exercise. So 1 implies 4 implies 1 is left as an exercise. They are just two lines, okay? So this was kind of tricky. The proof I gave is slightly different than the one in the book, but you know, doesn't matter. So you have two different proofs. All right. Now we have so-called homeomorphisms. Okay, so let me give this as a definition. Okay. Let x and y be topological spaces. A continuous bijection f from x to y is called a homeomorphism if f inverse from y to x is also continuous. So, what's a homeomorphism? Homeomorphism is a function between two spaces, but it has to be a bijection. So it is one-to-one and onto. So this means set-wise, these are the same things, right? It's a bijection. And moreover, their open sets are the same. Why is that? Because both f and f inverse are continuous. This means whenever you have an open set here, its inverse image here is an open set, and whenever you have an open set here, its inverse image is open here, and inverse image under f inverse is just the image under f, right? So this means not only the sets are the same, actually the topologies are the same. Okay, so if you have a homeomorphism between two spaces, this means they are the same space, only the names of the points are different. Okay, but uh, topologically they are the same, right? The sets are the same. There is a bijection, only the points have different names, and also the open sets are the same. Okay, so homeomorphism is something really strong. However, the condition that f is a bijection plus continuous doesn't imply that f is a homeomorphism, right? There are different conditions. The inverse map has to be continuous also. Let me give a quick example. So let f be the identity map. Identity map. Yani f of x equals x for all x in x, where x is the topological space. X şu olsun. A, B, and okay. And şöyle diyeyim şuna. F x tau 1, x tau 2. And tau 1 is this topological space. So empty set A, AB, and tau 2 is this topological space. Empty set A, it's indiscrete topology. All right. Well, then f is clearly continuous, right? Inverse image of the empty set is the empty set. Inverse image of AB is the AB. So I have just two open sets, and inverse images of these open sets are open. Therefore, the bijection, f is a bijection, it is the identity map, it is continuous. But the inverse map is not continuous, right? Then the bijection f is clearly continuous. However, f inverse from x tau 2 to x tau 1 is not continuous. Okay, why is that? Because what is the inverse image of this open set? Inverse image of the şuna G diyelim. Let me call it G. Inverse image of A. Well, inverse image of F inverse, since F is a bijection, this is nothing but F of A, and this is A, and this set is not open in tau 2, which is not open in tau 2. Hence, F is not a homeomorphism. is not a homeomorphism. So a one-to-one and on-to bijection may not be a homeomorphism. Okay. All right. Let me also talk about embedding, topological embedding definition. A function, uh, a function f from a space into another is called an embedding if the function, if f is a homeomorphism onto its image f of x, which is a subset of y, of course, considered as a subspace, considered as a subspace of y. So what I mean, okay, so here is, let's say, x, okay, and its image is this f of x inside a bigger space, probably, okay, y, and I consider f of x as a subspace of y, okay. So what are the open sets of f of x? They are the open subsets of y intersected with f of x. So an open set here is something like this, and f from this set to this set is a homeomorphism. So for example, inverse image of this open set is something like this, okay. So if this is the case, then we call it f an embedding, a topological embedding. So f has to be a homeomorphism from x onto f of x, where f of x is endowed with the subspace topology. Okay. Sorusu olan var mı? Any questions? All right. So let me give you some examples. Actually, I will give you one example. Okay, now consider the map F from okay, R standard into R2 standard described as below. So what is this map? It is this one. I have this R standard. Okay. And F takes this into the following to figure 8. So okay. So this 0 is mapped to this point, and the negative x-axis is mapped to this portion of the figure 8, and this uh, portion of the real line, the positive x-axis, is mapped to this portion. Okay. So for example, let's say -1 is here, 1 is here. So f of -1 is somewhere here, and f of 1 is somewhere here. And this point is 0. So f of 0, f of 0. Okay. Well, this f is clearly 1 to 1, 1 to 1. Although here I draw this, as if it never touches to this point, it doesn't, but the image looks like this, right? It actually ends here, right? Because as t goes to minus infinity, it will come back to this point, and the same thing here. Okay, so what you see here is the real figure 8. This is 1 to 1, and onto its image. Okay, its image. Moreover, it is continuous. Uh, f is also continuous. Why is that? Well, one can actually write down an expression for this. You know, I may not now at the moment, but one can do that. Let's see why this is continuous. So it is enough to check. Well, actually, I haven't proved that yet, but it is enough to check actually inverse image of basis elements are open, right? Inverse images of actually we have to check inverse image of every open set, but every open set is a union of basic open sets, right? Like balls. So it is enough to check continuity just for balls, as in the case of metric spaces. So if I choose a ball like this, what is the inverse image of this? Well, it is the empty set, which is open. If I choose a ball like this, inverse image is open because it is empty set. If I choose a ball like this, then inverse image will be something like this, right? And if I choose an open set like this, then inverse image will be something like this, right? Here, of course, this open ball intersect with the image is this, and this open ball intersected with f of x is this set. So this is my f of x, considered as a subspace of R2 with the standard topology. So these are open sets. I can also consider a third kind of open set. How? Let's consider this open set. An open set around the origin. So an open set like this. What will be the inverse image of this? Well, inverse image of this has 4 pieces. One piece like this, actually one piece like this, so that corresponds to an interval like this, and then another piece like this and another piece like that. So it means I have this piece and, okay, let me say I have this piece. Okay, and you see all of these are open sets, right? Inverse images of all these balls are open. So F is continuous. It is one-to-one and onto. So we wonder if F is an embedding. So question, sor. Singular nasıl? Yok ama burada şimdi daha homeomorfizm kurmadım ama. Zaten homeomorfik değil bunlar. Map continuous ama homeomorfizm olmayacak. Yok. Is F an embedding? Okay. So means what? I have so we have this map from F from our standard to its image, which is this figure 8. Let me call it Y, okay, as a subset of R2 standard. So figure 8 is my f of x, or f of r, I should say. Okay. Is it an embedding? Answer is no. No. This means what? F inverse is not continuous. F is indeed, F inverse is not continuous. Why is that? Well, you see, let G to be F inverse. Okay, so where is this point? Where is this defined? This is defined from Y into R standard, right? Y is being the image. So from this circle, I go in the opposite direction to R standard, and this map is not continuous. Well, let's see why it is not continuous. So let me write figure 8 here. Okay, so this is my Y inside R2, and I have G, which is F inverse into R standard. And I claim this is not an open, this is not continuous. Why is that? Well, let's take nasıl? Aha. Ama öyle bir bol yok. Burada diyorsun değil mi? Şu sarı bolu. Böyle bir bol çizemezsin ki. Ben burada bunu orijini içeren bir tane çizdim. Orijini içerecek. Orijini içeren bir şey de illaki böyle olmak zorunda. Orijini içermeyecekse o zaman ya bu mavi gibi ya da kırmızı gibi olmalı. Hani uzakta çizdim ama yani burada da çizsem aynı şekilde çizerdim onu. Daha sistematik olarak şimdi göreceğiz zaten niye şey olmadığını. Şimdi böyle bir open set alalım. Şu open set alalım. Bunun inverse imajı nedir? So let's say you to be this open set. What is the inverse image of this? Inverse image of this under f prime. It means what? The set of all points here that are mapped here. But if you remember, so this interval here is mapped to where? That is mapped into this piece, right? So I go like this, and so inverse image of this interval is the image of this interval under f, and it is this piece. So inverse image of this is just this piece. Okay. Bu muydu, öbürü müydü? Pardon. Evet, oydu. So here we have and this gadget, so this G inverse of U, which is equal to F of U, nothing else but F of U. Okay, this is not open in Y. So claim G inverse of U, which is F of U, is not open in the subspace space Y. Why is that? Why is that? The reason is very simple. If you choose for this to be open, it has to be what? It has to be intersection of an open set with the subspace Y. Well, if there is an open set containing this orange segment, it should contain the origin also, right? And any open set containing the origin contains a ball containing the origin. So that ball is something like this. Şöyle bir renk seçeyim ona da. Yeşil olsun. Right? Any ball containing the origin is something like this. But intersection of this ball with the figure 8 is not only the orange piece, but also it has these two segments, right? These pieces. So inverse image of, not inverse image, sorry, intersection of this ball with Y contains more than this orange piece. Therefore, the orange piece itself is not open in the subspace topology. Okay? Let me say one more time. If this orange piece, f of u, were open in the subspace topology, then this orange piece would be the intersection of an open set in R2 with figure 8. But any open set containing this orange piece contains the origin, and if it contains the origin, then there should be a ball around that origin which lies in that open set. A ball around the origin is something like this, and such a ball contains not just this orange segment, but also this two infinite rays, right? Infinite green rays. Therefore, this thing itself cannot be open in the subspace topology. Okay. Therefore, F inverse is not open. Hence, F F is not open değil. F so G, which is F inverse, is not continuous. And F is not a homeomorphism. Okay, F is not a homeomorphism. However, we can do the following. Okay, we can do the following. Let me write as a remark. I have this one-to-one bijection, right? There is this bijection F, and it is continuous. It is not maybe homeomorphism, but it is continuous. However, I can do the following. I can introduce a new topology on R so that this becomes a homeomorphism. So that this means what? I can introduce a topology on R so that with that topology, it is homeomorphic to figure 8. In other words, I can put a topology on R so that it becomes figure 8. Okay? And what is that topology? We almost described what that topology is. Open sets of this topology will be or a basis for this topology will have three kinds of open sets. Open sets of this type, the blue open intervals, red open intervals, and a third kind of open sets or basis elements. What are they? Open intervals containing the origin, but whenever you have such an open set, then you have to take two infinite open rays. One going to the plus infinity, the other one is going to the minus infinity. And I see this topology exactly from this picture and the bijection. So here is the remark I would like to write. Note that the following collection B is a basis for a topology on the set R. So I consider real line with as a set, and I describe this collection. So what's this collection? Blue intervals, what are they? A, B, where A and B are both negative. So the product is negative. This kind of intervals. And then this kind of intervals, A, B, are positive. These are the red ones. Okay. Blue ones, red ones, and then I have this orange ones. What kind of intervals they are? Union orange ones, A, B, but they don't come whenever you have an interval containing the origin, it has two tails. One tail going to the infinity and the other tail going to the minus infinity. Okay. Here A, B bu yanlış oldu. Her ikisi de negatif, her ikisi de pozitif diyecektim. A, B negatif. Ha zaten öyle dedim. Tamam. A, B pozitif. Tamam. Burada ise şunu söylüyorum. A çarpı B negatif. So A times B is negative. It means that one of them is positive, the other one is negative. Ya da isterseniz öyle yazayım ya. A negatif, B pozitif. C ve D rastgele reel sayılar. Now, so this one is the collection of those orange sets. These are the blue intervals. These are the red intervals. And all together they form a topology. They form a basis for a topology. And with this topology generated by this gadget, if let's say tau is the topology generated by this basis, then f from R with this topology into figure 8 as a subspace of R2 standard is a homeomorphism. Okay, so this is, I think, amazing, right? You have real line, you change the topology, and it becomes figure 8. And one nice thing about is that you see all these open intervals are open subsets of standard topology, right? They are just open intervals. So clearly, this tau is what? Well, weaker than the than our standard. So our standard has more open sets. Okay, if I take out some open sets, it becomes weaker, and if you just take out some sets carefully, it becomes figure 8, right? So if, for example, this is the basis, then it is figure 8. You see, an interval of only this type, where A is negative, B is positive, is not open in this weaker topology, right? This is open only if I add these two pieces. That's why, this is weaker. It has this thing itself is not open. This thing is open, this is open, but this thing itself is not open. All right. Any questions so far? Well, no. Here, my basis elements have this form. Of course, they are unions of these intervals, but in my topology, such an interval AB, where A is negative and B is positive, is not considered as an open set, okay, in my topology. This will be considered as an open set only if it is a part of a union like this. So this thing is considered as a basic open set, not only this one. This one is open because this is the union of growing intervals in the positive side. And they are in my basis already. So I can write any interval like this, C infinity, as a union of intervals A, B, where A and B are both positive. And similarly, this interval is a union of intervals of this type. Therefore, this thing itself is open in the topology. This thing is itself is open itself, right, in our topology. However, this thing, AB, where A is negative and B is positive, is not open in the in our topology. Okay. My open sets are this kind of unions. I cannot write this as the union of AB's, union C infinities, union minus infinity D's. And they are different objects. My objects are these unions, not right. I mean, uh, so this set is not equal to the union of this set. Because I don't declare that to be open. Okay, that's my choice. I say this is not open. Okay, only this thing is open. But then you may ask the following question. I mean, is there such a topology, right? I mean, maybe I say you are open, you are not open. That one is open. I can do this, but it's a legitimate question that, why such a thing is a topology, why it defines a topology. Well, this defines a topology. You can check that, right? You can check that this is a basis for a topology. And there is a actually good reason why this is a topology, because with that topology actually it becomes figure eight. Okay, so figure eight uh, is a copy of real line, right? Figure eight, this is a copy of real line. Although it intersects itself, this is a copy of real line. The only difference between them, so there's a bijection between these two. There's a bijection between these two. The only difference is that this guy has more open sets, okay, than this one. So set wise they are the same, but one of them has more open sets. So a straight object, if you with less open sets, maybe not straight at all, right? It may be figure eight. Well, think about this, okay? It is not difficult, but you have to spend some time and convince yourself somehow. And if you cannot, then again ask me. Sorusu olan var mı arkadaşlar? Any further questions? Okay, then let me stop here.